Hello everyone, my name is Minsun John. Today I'll be presenting Seeing Through the Blur, Unlocking Defocus Maps for Deepfake Detection. This research was conducted during my master's program in Computer Science and Engineering at Sungkyunkwan University and is scheduled to be presented at the upcoming CIKM 2025 this November. Before I begin, I'd like to briefly introduce the lab where I completed my degree. I'm an alumna of the Dash Lab, advised by Professor Simon Wu. Our lab's core mission is to solve social problems like deepfakes with artificial intelligence and contribute to solving real-world challenges. Our main research areas include the multimodal deepfake detection, machine learning to grant the right to be forgotten, and time series anomaly detection, which is crucial for industrial applications. Here is the outline of today's presentation. I will begin with a brief introduction to the problem of deepfake detection, followed by some background on defocus blur and related work. Then I will define our research question and explain the methodology we designed to answer them. After that, I will share the experimental results, and finally, I will conclude with the key findings. My research addressed the critical challenges of deepfake detection. This is a significant social issue, as these hyper-realistic fakes can be used for malicious purpose, from spreading fake news to committing crimes, threatening the very integrity of our visual media. The technical difficulty lies in the rapid advance of generative models. It has become increasingly easy to create fake images that look realistic, sometimes even more perfect than real ones. For instance, this slide shows a real photo on the right and an AI-generated portrait on the left. Both appear visually convincing. This raises a fundamental question. When everything looks real, what truly defines an authentic images? The key lies in how the image is created. Real images are captured through a physical device, a camera, that operates according to the rules of optics. In contrast, fake images are generated digitally, and while they may appear blurry, that blur is often artificially added for aesthetics and lacks physics accuracy. So to detect what's real, we turn to something that only real cameras can produce. Defocus blur. What exactly is defocus blur? As you can see in this autofocus photo, it's the blur that occurs when parts of a scene are out of focus. This phenomenon is governed by a principle called depth of field, or DOF, which is determined by the camera's aperture settings. Now let's see how changing the aperture affects blur in real images. At aperture f2.8, the depth of field is very shallow. Only the girl is in focus, and both the foreground and background appear blurry. At f5.6, the pen and the girl are both in focus. Finally, at f11, the depth of field becomes much deeper. It looks like the entire scene, including the bookshelf, is in focus. But in reality, due to the optical limits, some areas are still slightly blurred. This creates predictable, physically consistent blur patterns that are a natural signature of the camera's lens and the scene's geometry. In other words, the blur in the rear photo isn't random. It's a predictable physical fingerprint, uniquely shaped by the scene's depth and the camera's lens. While AI excels at creating visually plausible 2D images, it struggles to perfectly simulate the complex physics of 3D depths and lens optics. As a result, AI-generated blur can often appear unnatural, ignore depth cues, or be physically inconsistent. Therefore, our core idea is to analyze these physical fingerprints of authentic blur to distinguish it from the artificial blur found in deepfakes. The principle is what sets our approach apart. Previous detection methods can be broadly categorized. RGB-based methods like exception model often function as uninterpretable black boxes. Frequency-based methods can detect artifacts, but may lose precise spatial information. Consequently, there is a growing need for interpretable features with a strong physical foundation. In contrast, our defocus-based approach is, first, physically grounded, as it relies on the universal principles of optics that we just discussed, and second, interpretable. Unlike a black box, our method allows us to visualize the defocus map and see precisely why the model made a decision. These advantages lead us to formulate three research questions to guide our study. Based on this idea, we define three research questions. Do defocus blur patterns differ between real and fake images? Second, can these patterns improve detection performance? Third, does the model actively use defocus features in its predictions? This is the overview of methodology. The core idea of our method is to explicitly extract the defocus blur signal, what we call the defocus feature, and use it for deepfake detection. To do this, we generate a defocus map by first applying the edge-based algorithm from Zhou and Shim, which calculates defocus from the ratio of two Gaussian gradient filters, and then refines this initial map with a fast-guided filter for improved accuracy. The final defocus map highlights blurry regions in white and sharp regions in black. Devise three types of feature-level analysis. First, we create a binary mask by subtracting the fake defocus map from the real one and thresholding values over 0.1. This highlights regions with noticeable blur differences. Second, we calculate local variance by using a sliding window and assign the variance around each center pixel. This helps capture local blur inconsistency across the image. Our assumption is that fake images contain abrupt changes in blur, unlike the smooth transition in real images. To validate this, we average the local variance across each images and perform a KS test, which confirms a statistically significant difference between real and fake distributions. Third, we applied TSNE to the extracted defocus features to examine their distribution in a low-dimensional space and assess how well they separate real and fake images. At the model level, we investigated whether our trained model actually leveraged the defocus information we provide. First, to visually demonstrate this, we use SHAP, a method from game theory that quantifies the contribution of each input region. It works by simulating the effect of removing each part of the input and measuring how the prediction changes. In this study, we apply gradient SHAP to both the RGB and defocus models and compare the resulting attribution maps. The purpose of this visualization is to show that the model's attention is concentrated on the physically manipulated regions. Second, to evaluate this quantitatively, we introduce two metrics, the shape alignment score and KL divergence. The alignment score measures how well the shape attribution overlaps with the actual blur discrepancies. A higher score means better alignments. The goal was to see if our model's focus aligned with the physical clues in the manipulated regions, which we will see in the result section. The scale divergence quantifies how far the shape distribution is from the actual blur difference. Lower KR means the model focuses more accurately on distorted areas. Together, these metrics help us assess whether the model's decisions are physically grounded. To test our method, we use two distinct datasets and detection pipelines. First, for defect detection on facial manipulations, we use the Face Forensic dataset. For this task, we adopted a defocus-only model using ExceptionNet. This setup allows us to test defocus as a standalone forensic signal. Second, for AIGC detection, we use the CINDOF dataset, which we customize with a balanced set of images containing either real camera captured defocus blur or synthetically generated blur. Here we propose a dual branch model that processes RGB and defocus features in parallel and views them using a Hadamard product before classification. On the FF++ dataset, our defocus-only model achieved an AUC of 0.99, outperforming strong RGB baselines like ExceptionNet. Our defocus-only model using the same exception backbone achieved a higher AUC by simply replacing RGB input with defocus maps. On the CINDOF dataset, integrating our defocus feature with an RGB feature, the dual branch model consistently improves accuracy and recall across all backbones, especially the accuracy of the exception model improved by 2.1%. This demonstrates that our defocus feature provides a powerful complementary signal that existing models often miss. We also prove the significance of our feature through tree analysis. We performed this analysis on 6,400 images pairs for each fake types in the Face Forensic dataset. First, the binary mask. Here we show an example of fake images on the left, real images in the center, and the resulting binary mask on the right. After comparing 6,400 image pairs, we found that real and fake images differ in defocus structure by around 5 to 10% of the pixels, suggesting defocus blur is a strong indicator of manipulation. To quantify blur inconsistency, we computed local variance maps for each image. Then we averaged each map into a single value and compared the distribution of 6,400 each real and fake images. The fake images show slightly higher variance on average, and a KS test confirms that the distributions are significantly different. Finally, we visualize the extracted defocus feature using TSNE. As shown here, real blue and fake red images form clearly separable clusters, demonstrating that defocus-based feature alone can distinguish between them effectively. Next is model-level analysis results. These sharp visualizations show that our model's rationale for its decisions, the red areas, precisely matches the manipulated face regions. We first compare sharp attribution maps from RGB model and the defocus-based model. In fake images, the defocus model shows more focused attention on manipulated regions such as facial areas, while the RGB model often highlights unrelated backgrounds. This suggests that defocus cues help the model better localize forgery artifacts. To validate this observation, we use our two quantitative metrics. For the alignment score, we compare where sharp attribution overlaps with actual difficult discrepancies. The purple bars indicate true distortion regions, and the yellow bars show where sharp is concentrated. We compared the average alignment score over 1,000 fake images for each manipulation type, and the difficult model shows consistently higher alignment score or samples. For K-R divergence, we measure how close the sharp distribution is to the actual difficult difference. Again, the difficult model shows lower divergence for most fake types, except face swap. This confirms that the model's attention aligns more closely with physically meaningful blur regions. To answer these questions, we make the following contributions. First, to the best of our knowledge, this is the first study to use defocus blur as the main signal for defect detection. Second, we show that the defocus blur captures structural difference between real and fake images through feature level analysis. Finally, we confirm that defocus-based models attend to physically meaningful regions. In summary, we proposed a defect detection framework based on defocus blur, a physically grounded and interpretable feature. We validated its effectiveness through feature level and model level analysis, addressing three key research questions. Our method achieves state-of-the-art results on FF++ and demonstrated improved performance on AI-GC tasks with RGB Fusion. We hope this will contribute to building more trustworthy media forensic systems. The references are as follows. I will conclude my presentation. Thank you for your attention.